Swayam Prabha. Digital India. Educated India.
So, in the last two lectures, I have given you some idea about different types of interfaces. At least I could convince you that the interfaces between crystals of similar compositions and structure can be different types. One of these is basically considered as a low angle gain boundaries. And I discussed to you about different types of low angle gain boundaries, tilt and twist. So, now as I told you, if the angle between the two grains, either it may be tilt or twist, is more than 10 to 15 degrees, then no longer the dislocation to accommodated along the gain boundaries can be tenable. So, in general, when the theta exceeds this value, then dislocation spacings become very small and the chords or dislocation start overlapping, and therefore, we can no longer have dislocation arranged in a parallel row, giving rise to a low angle gain boundary. And at this stage, most of the gain boundaries actually are known as high angle gain boundaries, and they are actually random. They cannot be treated as a very systematic way, just like normal low angle gain boundaries. Basically, in a low angle gain boundaries, there are regions of fit, the atomic fit in most of the cases only at the cores or dislocations atomic fit, the fit between the two grains are not proper. But in high angle random gain boundaries, the number of these unfit regions where the atoms of the two grains are not able to fit each other are more. And in a bubble wrapped model, that can be easily seen, that you see along the gain boundaries of high angle, this is what I am marking by using a pen, is there are large number of misfit regions where atoms both the grains do not fit each other. And this is basically the feature of random high angle gain boundaries. That is why the high angle gain boundaries are not discussed much in the literature, because exact atomic matching or atomic arrangements along these gain boundaries are not yet resolved. Nobody understands how atoms can actually coexist along these boundaries. What we can do is the next few slides to make you understand there are some special cases of these kind of boundaries where the angles are more than 10 to 15 degrees, but atomic fitting or atomic match is possible. That is what I am going to show you for the next few cases. Okay, let us take the special high angle gain boundaries. One such high angle gain boundary is known as a twin boundary. As you have seen in the low angle gain boundaries, the misfit between the two grains, orientation misfit, can be accommodated by arranging dislocations at a particular interval. In same way, twins can also be used to form special high angle gain boundaries. Okay, let us discuss what is a twin. Twin is nothing but a special arrangement of atoms when one part of the crystal becomes mirror image to the other part of the crystal along a boundary. And this is one of the dominating deformation mechanism in the many of the hexagonal crystals. Few cubic crystals also show twinning, but there may be different types of twins. But whatever it is, twin is one of the predominant mechanisms of deformations in many of the metals or even alloys. So, if a twin boundary, we are talking about twin boundaries, right. So, a twin boundary is parallel to the twin plane. So, what is a twin plane? Here it is shown here, there is a twin plane along these dotted line. You can see here the atomic planes have distorted or rather deformed in such a way that if I place a mirror along the twin boundary, the one set of planes become mirror image to the other set of planes. That is what is a twin boundary. So, if this twin boundary actually is parallel to the twinning plane, twin boundary means boundary along the gain boundary. If it is parallel to the twin plane, then atoms will fit perfectly along in both the grains. Suppose this is grain 1 and this is grain 2. Okay. So, what is happening here? Along this twin boundary, which is parallel to the twin plane also here, the atoms fit exactly nicely. There is not even a single misfit along the boundary. That means you do not need any misfit dislocations to accommodate any kind of difference in the atomic fitting. Such a kind of boundary is known as coherent twin boundaries, because atoms are matching perfectly with each other, atomic planes. Only thing which makes them different is that orientations are changing from grain 1 to grain 2, and the change of orientation is basically twin related. So, this kind of boundaries where there is an exact match of the atomic planes will have very low energy. In fact, energy can be as low as 1 millijoule per meter square. So, energy of a coherent twin boundary is extremely low. In fact, in the literature nowadays people are working on mechanical behavior of material in such a way that boundaries can be made like a coherent twin boundaries. Then energy of the boundaries are very low, so therefore grains will not grow. Not even that, you can actually make the many interesting phenomena understandable, like grain growth or recrystallizations, if you create such a kind of grain boundaries predominantly in a material. But this is basically such a kind of situation when a twin boundary is exactly falling on the twin plane is a very odd situation. Normally is very rarely happen, but it do happen some cases. Excuse me. So, if the twin boundary does not lie, suppose parallel to the twin plane, what will happen? One such thing is shown here. You see a twin boundary is here, this is a twin plane, okay. This is the twin plane, twinning is shown, and the boundary is somewhere a solid line, this is the boundary. So, therefore, twin plane and the twin boundary are not same, they are at an angle each other. So, that angle is given by phi. Now, in such a case what happens? If such a case happens, you will see there are places where the atomic planes match. Suppose here I am marking, okay, marking here, there, you see it matches. But as you go away from this, the the planes are not matching. There is a distance, there is a basically definite mismatch of the atomic planes coming from the grains G1 to G2, okay, very clearly seen. So, what that means what? That means these bonds here atoms sitting at these positions are not dissatisfied by the bonds, by the atoms on the grain 2, and this is known as incoherent twin boundary, because atomic planes are not matching for all the planes. Rows of atoms on the grain G1 is not matching with many of the rows of atoms are not matching with grain D2, and this leads to increase of the interfacial energy, again boundary energy, because these satisfied bonds which are there along the boundary will lead to increase in the energy. So, energy of a twin bound is very sensitive to the orientations, that is what you see here. In such a case of first case where there is a coherent twin boundary, energy will be very low, but the moment I change the twinning plane and the boundary plane, they are distinctly different, then the energy will be higher. So, that means it depends on this value phi, which is the angle between the twinning plane and the boundary plane. And if this energy is in certain value, if I plot a gamma versus theta or versus phi here, for certain values of the phi of this theta, or not phi, theta actually, this theta, you see that the energy becomes very low, and that is why the coherent twins form. So, therefore, coherent twins will have orders of magnitude lower energy values than compared to incoherent twins, and this is why it is very important. That is why it is better actually we create grain boundaries which are semi coherent type, and so that these kind of situations, this kind of energetics can be preferred. So, this is a very special grain boundary. Okay. Now, to give you some energy values for different crystals like copper, silver, or maybe stainless steel. Stainless steel is one of the classic case. In a coherent twin boundaries you see here is basically for the copper is basically only 21, silver is lower, but stainless steel is about 19, very close to 20 millijoule per meter square. Now, incoherent twin boundary on the other hand is one order of magnitude higher, it is about 500 or 100, at least 100, and normal grain boundaries which are actually even much higher. So, therefore, it is very clear that if you have twin oriented grain boundaries which even the angles are high, 10 to 15 degrees or higher, still I can actually have a very low grain boundary energy. That is one part. Okay. Now, let us look into in a little bit detail about these special grain boundaries, and let us consider FCC crystals. when two grains in a FCC crystal are suppose related by rotation along 1 0 0 axis, okay, that is what is shown here. Now, the most high angle gain boundaries have the same energy and should have a relative disorder structure. That is because of that is mainly because of the random, these are random boundaries. Now, when the two gains are related by rotation about 1 0 axis, there are several large angle gain boundaries which can be significantly low energies. So, that means what I am talking now is orientation dependence. If two gains are suppose related by rotation along 1 0 0 axis, that is the one of the cube axes, then this very difficult to actually make them low angle low energy, because they will be very little leeway to create such a kind of twin boundaries. But when they are related by rotation along 1 0 axis, okay, that is one of the phase diagonals, then what else? There are several large angle gain boundary orientations which can have lower energy, like one which is shown as 70.0 degrees. Okay, 70.0 degrees is a specific case. This corresponds to a coherent twin boundaries. We know that the FCC crystals, the twins, if they are related by 1 1 0, the angle becomes actually 70.5 degrees. The reason is for these boundaries not yet understood. Why? Because whether it is really that these boundaries has a perfect atomic match or not, people have tried to do some electron microscopy, but it is not clear. But it seems the atomic the planes do match nicely, that is why they can be created. And these are the things which are shown here. You see here, this is a gamma plot again. This is the gamma versus relative bound energies versus the orientations. You see, this is one low, another low, okay. And similarly, so there is another low here. So these angles, which this is 70.5, this is about 140, 141 actually, and the other one is about 178. So these angles, if the boundaries are related along 1 1 0 axis, then they actually form very low energy boundaries in FCC crystals. Now, upon giving you, so I have given you fair amount idea, although it is not possible to discuss about all the high angle gain boundaries. Some of them are really very complex, but real microstructure consists of many grains. They are not actually only one boundary or two boundaries. There are thousands of grains in real microstructures, and each grain is oriented differently from the other grain. So therefore, the boundary, nature of the boundaries of all these grains which will have with the neighbors will change based on type of orientations they have, even chemistry also. So it shows austenitic stainless steel on the right side. You see, what do you see here? You see it contains low angle gain boundaries, high angle gain boundaries, as well also twin boundaries. You see, these are the twins. Okay. So in case of stainless steel, there are many twins exist. So therefore, you have all kinds of boundaries. But remember, we are looking at, when we are looking at a microstructure in optical or SEM, we are looking at 2-dimensional picture. It is not that we are looking at 3-dimensional. So therefore, but most of the grains are actually 3-dimensional entities. So the boundary we need to look at, if we really want to get the characteristics of the atomic matching, we need to look at the z axis also, not only x and y, but z axis also. So in a 2-dimensional picture, what all you see? You see the grains can meet along a boundary or in a plane. That is what is a gain boundaries. This is a gain boundary. In a 3 grains can meet at a line. Okay, I don't know whether it's there or yeah, it's there. There's one grain here, there's another grain here, there's another grain. See, the 3 grains are meeting along this line. Okay, and also 4 grains can meet at a point. Whether it's there or not, let's see. 4 grains meeting at a point somewhere there. 1, 2, 3, 4. Yes, no, it's not there. Most of the cases. So very rarely you see that kind of 4 grains meeting at a point, but you can see many times 3 grains are meeting at a point. Okay, these are the points at which 3 grains meets. So therefore, what is important point I am trying to convey is that not only the boundaries, but also these edges or the corners actually, or the meeting points, they also lead to an energy of the system, because it is not possible to always have perfect or semi-perfect atomic matching at these points. So finally, energy of the whole polycrystalline material will be summation of the boundaries, different boundaries, whether it is a high angle, low angle or twin boundary, or even and additionally on these points in which these grains will do meet, okay, 3 grains or 2 grains. Remember, when you are trying to have 3 grains meeting along a line or a point, it is very extremely unlikely that the atomic planes will be at a very low energy configurations at these points. So, therefore, finally, in a nutshell, what I can say is that real polycrystalline crystals are much more complex than we think about it. Although we can talk about interfaces separately like grain boundaries and other things, but real grain structures are much more difficult, and that is why actually a lot of engineering comes into picture. You can do many engineering to modify these boundaries and create different kinds of materials. Okay, so I will skip this part because this will come later. So, what I will do is now I will go to the interfaces, okay, boundary between interfaces. These are the things which will come later when you discuss about the recrystallization and grain growth. So, let me just start and say that so far we have discussed about the boundaries between crystals of same type, same chemical compositions like in pure metals, okay. But you can have boundaries between 2 different phases, and these are the boundaries which are more important. Okay. By the way, before I go into details of that, the boundaries which we have seen so far, high angle, low angle boundaries also will exist in these solids, but in additional to that there will be boundaries which will be between 2 separate phases. Okay, so there are different types of things which we will be talking about it. We will talk about, first of all, we will talk about whenever you have 2 different phases, what is the interface coherence, how the interface between the 2 phases can be made coherent, and if they are not coherent, well, what are the different possibilities will exist. Whether we can actually discuss, I do not know whether we will get time in this lecture or the next lecture, but we have to discuss somewhere because space hardening depends on second phase shape and how we can actually get those, and whether we can have a coherency loss, what will happen if I have a loss of coherency along the boundaries, and finally we possibly will discuss about the Giselle interfaces. Interface boundaries in solids, basically interface boundary means between you have a alpha phase suppose, and inside you have beta, that between them the boundary is known as interface boundary, because they are 2 separate phases, they have different crystal structures, they have different chemistry. So, therefore, we cannot no longer talk about this is a grain boundary between alpha and beta. We always say this is a phase boundary between alpha and beta. So, these such boundaries can be of 3 different types, at least we have some idea about that in basic material science. Depending on the atomic structure across the boundaries, it can be either coherent type, semi-coherent type, incoherent type. Right now, it is not possible for you to understand what are these, but they are the 3 divisive classes which we will be talking about it in next. Well, whenever we talk about 2 crystals, see, alpha is a crystal, beta is a crystal, because alpha is a grain of alpha type, beta is a grain of beta type. So, there are 2 separate crystals, that is why they are separate grains of different phase, different chemistry. It is possible that in a very nice situation where the planes of alpha across the boundary will be exactly matching the planes of beta. Okay, that is what is shown here. You see, there is a boundary A prime and B prime between the alpha and beta phases, and you see the atomic spacing in such way they are oriented. Let us suppose that can happen, it can happen actually, do happen, I will give example also, such a way that A alpha, that is the distance between the planes of the atoms in the alpha phase, and A beta, distance between the planes in the beta phase, are exactly same. Okay. So, obviously, if this can happen in many cases, it does not require that both of them should have similar crystal structure. If it is, it's good, if it is not, still it can happen. So, this such a kind of boundary where the atomic bonds are exactly satisfied is known as a fully coherent interface, okay, because 2 lattices are continuous across the interface. Now, what is the energy of the boundary is due to? Mainly due to the chemical differences across the boundary. See, here in the beta phase, all the atoms are white color, okay, or white kind of balls. On the alpha phase they are actually black. But so therefore, inside the alpha phase the bonds are basically between black and black, inside the beta phase between white and white, but at the interface the bonds are basically between alpha and black and white. So therefore, bond characteristic has changed. So such a kind of energy you will have, such a kind of boundary will have energy because of these kind of difference in the bonds. That means the bonds are actually varying across these boundary, changed the chemistry. So therefore, basically energy of this kind of system, energy of this kind of what do I say, this kind of structure or boundary structure will be basically because of chemical type, which is known as gamma chemical, because bond type has changed across the boundary. So disregarding the chemical pieces, crystal interface can only be achieved if listen carefully, if interfacial plane has the same atomic configuration in the both phases, and that means this requires the two crystals to be oriented relatively each other in a very special way. They has to be related in a very special way, otherwise this kind of situation will not occur. You know, in a copper silicon system such a kind of thing happens. Silicon rich phase, which is called kappa, is basically having a hexagonal crystal structure. On the other hand, copper silicon phase has a FCC crystal structure. Whenever kappa phase, which is silicon rich, forms within this copper silicon FCC phase, the interfaces are arranged in such way 111 plane of FCC's copper silicon will be parallel to 0001 plane of HCP kappa phase. And these two planes, it seems they are so nicely matched, their d spacings, the d value of the 111 planes in the copper silicon FCC phase exactly same as the d value of 0001 plane of HCP kappa phase. And because of that, there is a complete lattice registry. That means the planes exactly fall on each other across the interface. And that is why, that is what I would say, such a kind of configuration is possible when two crystals are oriented related to each other in a very special way. Okay. You know, this is you see, this is what one situation. Another situation is shown on the right side, that is known as B, where the planes are not parallel, okay, but atomically matched. You see, the planes in the alpha phase, they are actually coming down from the top to bottom, but on the other planes on the beta phase, they are moving at an angle with respect to the interface, but still they satisfy all the bonds at the interface. So therefore, either such a kind of orientation, I am showing only over two, there may be some other possible, either first type of orientation when planes are across the boundaries are parallel to each other, or the planes across the boundaries are actually at an angle to each other, but in both the cases the certain planes has to be oriented parallel to each other, then only this kind of coherency can happen. So coherency means that atomic planes must be satisfying their bonds across the interface, all the bonds, then only coherency is possible, otherwise coherency has no meaning. Okay, so whatever the situation, whether A or B exists in the real crystal, actually the interfacial energy or the energy of the boundary is basically coming from the chemical part of that. There is no structural distortion of the bonds, or there is nothing because of the perfect lattice registry. So because of that, structural part of the interfacial energy is basically vanishingly zero, small, only chemical part exists in such a kind of situations. Well, let me see what is next there. So, you know, as the interface, let us complete this part, then we can move on to the next class about the incoherent and coherent semi-coherent interfaces. At the interface, there is usually change in composition, that is what I told you just now, because atoms are changing from the white to the black, and so therefore energy is only because of chemical. Energies of these boundaries are basically normally maximum up to 200 millijoules. It can vary from actually 10 to 200 millijoules per meter square. When the interface between the atoms is, suppose you can have a situation, interface, the distance between the atoms in the interface is not identical. Suppose in the alpha phase distance is this much, beta phase is little bit higher. Still it is possible to maintain the coherency by straining one of the lattice. Like here you can see beta has been strained more than the alpha. So basically atomic planes on the both of the interface has been strained little bit, that means bonds have been distorted a little bit on the both sides. Okay. and this kind of distortion we always define as a coherency strain. Strain in order to maintain the coherency across the interface. It is better for the system to distort the bonds than to leave behind unsatisfied bonds. It is always better, and that is why such a kind of systems, it do happens in precipitation under alloys. Such a kind of situation actually arises like aluminum copper system. Such a kind of boundary can exist, and this boundaries also has a low energy, but not as low as 200 millijoule per meter square, little bit higher than that. And in this situation, obviously the gamma, the total interfacial energy between the two boundaries basically because of both chemical part as well as structural part, and structural part is coming from the distortion of the bonds. That is basically strain energy. And these strain energies are basically normally may not be perfectly plastic, maybe it's elastic also. Whatever may be the situation, strain energy will do exist along these boundaries, and this needs to increase of the boundary energy. So, interference coherency, as you see, can be still attained even if the lattice plane spacings are not matching perfectly along the interface. System will try to attain such a kind of configuration in order to reduce the energy of the system, but in many cases it may not be possible. Okay. So, that is what I am showing here. So, let us stop here and we will carry over the discussions about the interference coherence and the semi-coherent and the incoherent boundaries in the next lecture.